Okay, so we're now going to use these concepts of stabilizer subgroup and orbit to give a formula for the number of elements in the polyhedral rotational symmetry groups. And you'll find that this is reminiscent of Lagrange's theorem. Lagrange's theorem said that the number of elements in a group is equal to the number of elements in a subgroup times the number of cosets corresponding to that subgroup. So you can go back and review Lagrange's theorem. Here we're going to do something very similar. Well, to illustrate this, let's go back to our familiar friend, the cube, and we'll consider the rotations around the x-axis. So we've used this example several times to show different things. Now, we know that there are 4 rotations around the x-axis, and we know that these stabilize the face x plus. So I'll use the picture down here, and let's just say this blue face is the face x plus. So think of the 4 rotations that stabilize this blue face, that take the blue face to itself. All right. So on the one hand, you have 4 elements in that stabilizer subgroup. On the other hand, this blue face has rotations that can take it to any other face. For instance, there's a rotation that takes this blue face to this green face, or the blue face to the yellow face, and so on. How many faces can this face go to? Well, there's 6 faces on the cube, and this blue face can go to any one of those faces. So that means there's 6 faces that this can go to, and I also have 4 rotations that leave this face fixed. Now, suppose I first rotate with one of these rotations, and then I rotate to move the face to another face. So for instance, suppose I first rotate this blue face 90 degrees, then I rotate the blue face up to the green face. You can see that that's actually going to be a different rotation from just rotating the blue face up to the green face. In fact, I can get 4 rotations that take the blue face to the green face by first rotating the blue face in such a way as to keep the blue face fixed, and then rotate it to the green face. For instance, I could rotate the blue face 180 degrees and then rotate it up to the green face. That's going to give me a different rotation as if I rotated the blue face 90 degrees and rotate up to the green face. So I have a choice of 4 rotations of the blue face to make first, and then I have a choice of moving that blue face to any one of 6 other faces. So that gives me 4 times 6. In general, I get this result. The order of the group G is the order of the group that stabilizes any particular set element times the size of the orbit of that set element. All right, that just generalizes the argument that I gave in particular for the cube. And here are some exercises to apply the same idea to other examples. Okay. For example, the stabilizer subgroup for the edge x plus z plus. All right, that would be this edge here. If this is x plus and this is z plus, this is the edge x plus z plus. How many group elements stabilize this edge? Well, I'll tell you that there are 2. You can figure out what they look like. In fact, there's a very good video. You go back here, and the link is back here. Sorry, go back up here. And this link in 13.2.1, I don't think you can click on this and make it work, but just copy and paste this link. It will show you the different rotations of the cube. It's an excellent video. So let me go back there. All right. All right, so there's an exercise. All right, so here we make the connection between this formula that we just arrived at, G equals the stabilizer subgroup order times the order of the orbit. that's very similar to Lagrange's theorem. Okay, so the order of a group is equal to the order of a subgroup times its index. So if we replace H with the stabilizer subgroup, we find out that we have order of G equals order of the stabilizer subgroup times the index of the stabilizer subgroup in the group. So this tells us that the order of the orbit is equal to the index of the stabilizer subgroup in the group. And the general statement is here that the order of an orbit is equal to the index of the stabilizer subgroup in the group. Now, let me give you some idea about the proof of the theorem. We're trying to show that the number of elements in the order of X is equal to the index of this subgroup Gx in the big group G. Now, this is the number of elements in a set of points in big X. This is the number of cosets of Gx in G. So here we're counting cosets, here we're counting points in the set big X. So a good way to show that these two sets have the same number of elements is to create a bijection. So we're going to create a bijection between elements of big X and cosets of the stabilizer subgroup. Now, if you think about the way I explain this formula, we can actually generalize that. What I said here was that to get any rotation, I can first rotate the blue face and then move the blue face to any other face. So notice that what that means is I'm applying a group element in Gx, and then I'm applying another group element which takes this X plus to something else. All right, so we're having a group followed by another element. That looks like a coset because I can take any group element and then follow it by another element that's not in the subgroup, but it's in the big group. So that actually looks like a coset. And in fact, any coset of the stabilizer subgroup of this face corresponds to all the rotations that take this blue face to another face. All right, so we have one coset for blue face to green face, one coset for blue face to yellow face, one coset for blue face to the face in back, and so on. So that's how we're going to construct the one-to-one correspondence. We're going to first take the elements of Gx, and then we're going to apply an element G which takes the element X to a particular Y. And we do this for every Y in the orbit. And then here we go through and show that this mapping defines a bijection between the elements of the orbit and the cosets of the stabilizer. All right. So I'm not going to go into the technical details, but that's the idea of the proof. All right, so that's it for that subsection.